Welcome to Fuzzy Mathematics, the basics. In the previous lectures, we have talked about several different lattices, such as Boolean algebras, soft algebras, and optimal soft algebras. Let's do some examples. First, example 1. Determine whether a Boolean algebra is a soft algebra. We know that a Boolean algebra is a complemented lattice together with distributivity. A soft algebra is a dual lattice together with boundedness and distributivity. They both have distributivity. Now suppose it is a Boolean algebra. Is it a dual lattice? A Boolean algebra obeys the double negation law and De Morgan laws, so it is a dual lattice. It is complemented, so it is bounded. That is, a Boolean algebra is a soft algebra. Next, example 2. Determine whether an optimal soft algebra is a soft algebra. An optimal soft algebra is a dual lattice, together with density and infinite distributivity. Both of them are dual lattices. Suppose it is an optimal soft algebra. It has infinite distributivity. It must be complete. Then it is bounded. Of course, infinite distributivity implies distributivity. That is, an optimal soft algebra is a soft algebra. We have known that a Boolean algebra is a soft algebra, and an optimal soft algebra is a soft algebra. Naturally, we may ask more questions, such as whether a Boolean algebra is an optimal soft algebra, whether an optimal soft algebra is a Boolean algebra, whether a soft algebra is a Boolean algebra, whether a soft algebra is an optimal soft algebra. By the end of this topic, you will find your own answers to all these questions. In this lecture, we are going to talk about a specific algebraic structure. We are going to talk about the poset, the closed interval from 0 to 1, together with less than or equal to relation. We will ask all kinds of questions, such as, is it a Boolean algebra? Is it a soft algebra? Is it an optimal soft algebra? To be specific, is it a lattice? If it is, what's the algebraic structure induced by this lattice? Is it distributive? Is it infinite distributive? Is it complete? Is it dense? And so forth. First, it is easy to see that the less than or equal to relation on the closed interval from 0 to 1 is a partial order. It is reflexive, antisymmetric, and transitive, so it is a partial order. The closed interval from 0 to 1, together with the partial order, is a poset. Next, is it a lattice? Determine whether each pair of real numbers in the closed interval from 0 to 1 has both a supremum and an infimum. Yes. What are they? Suppose A and B are two real numbers in the closed interval from 0 to 1. The supremum of A and B is the same as the maximum of A and B. The infimum of A and B is the same as the minimum of A and B. So it is a lattice. And this is the algebraic structure induced by this lattice. In this case, the join of A and B is the same as the supremum of A and B, the same as the maximum of A and B, and the mean of A and B is the same as the infimum of A and B, the same as the minimum of A and B. The notations used here are consistent with those that we are familiar with. The relationship between the partial order and the two binary operations is as follows. A is less than or equal to B if and only if the join of A and B is B, if and only if the meet of A and B is A. Next, we are going to talk about the properties of the two binary operations in this algebraic structure. For example, the idempotent laws, the commutative laws, the associative laws, and the absorption laws. Shall we need to prove them? No. This algebraic structure is induced by the lattice. It obeys these rules. In this algebraic structure, the following laws hold true: the idempotent laws, the commutative laws, the associative laws, and the absorption laws. Next, boundedness. Does H have a greatest element? Yes. Its greatest element is 1. Does H have a least element? Yes. Its least element is 0. Is H bounded? Yes. It is a bounded lattice. 0 is less than or equal to A, less than or equal to 1 for all elements A in the closed interval from 0 to 1. By the definition of the greatest element and the least element, we have the domination laws and the identity laws hold. That is, the join of A and 1 equals 1. The meet of A and 0 equals 0. The join of A and 0 equals A. The meet of A and 1 equals A. Maybe that's the reason why the domination laws are also called 0-1 laws. Next, we will check the completeness of this lattice. Is H complete? Each non-empty subset of the closed interval from 0 to 1 has both a supremum and an infimum, so it is a complete lattice. In addition, we define the supremum of the empty set is 0. The infimum of the empty set is 1. Next, we are going to talk about the distributivity of this algebraic structure. This lattice obeys the distributive laws. Actually, it obeys the infinite distributive laws. Meet distribute over join, join distribute over meet. Or we can say infimum distribute over supremum, supremum distribute over infimum. We can prove these equalities using the antisymmetry of real numbers, but we won't do that here. Next, we will define a unary operation complementation on the closed interval from 0 to 1. Define the complement of A is equal to 1 minus A. Is H a complemented lattice? A lattice is complemented if and only if each element in this lattice has at least one complement. Determine whether the supremum of A and the complement of A is equal to 1, and whether the infimum of A and the complement of A is equal to 0. Let's check. Suppose 0 is less than A, less than 1. Then 0 is less than the complement of A, less than 1. So 0 is less than the maximum of A and the complement of A, less than 1. And 0 is less than the minimum of A and the complement of A, less than 1. Therefore, the complementary laws do not hold in this lattice. Wait a minute. Maybe the unary operation here is not the right one. Maybe we can find a better one, such that there exists a complement for each real number in the closed interval from 0 to 1. Could we check every possibility? No, we can't. We can't check every possibility. But we can prove that there exists no complement for each real number a in the open interval from 0 to 1 in this lattice. We can prove it by contradiction. Suppose a is a real number, 0 is less than a, less than 1, and assume that b is a complement of a. Using the definition of complement of an element, we have the maximum of a and b is 1, and the minimum of a and b is 0. Because a is less than 1, and the maximum of a and b is 1, so b equals 1. Because 0 is less than a, and the minimum of a and b is 0, so b equals 0. Contradiction. There exists no complement for each real number a in the open interval from 0 to 1 in this lattice. Now back to the unary operation we have defined on the closed interval from 0 to 1. For all elements a in the closed interval from 0 to 1, define the complement of a is 1 minus a. It is still called the complement of element a. In the algebraic structure, the complementary laws do not hold, but the double negation law holds. By the definition of complementation, we have the complement of a equals 1 minus the complement of a. Again, by the definition of complementation, it is going to be 1 minus a, which is a. This completes the proof. Next, the De Morgan laws. This lattice obeys the De Morgan laws. The complement of the maximum equals the minimum of the complements. The complement of the minimum equals the maximum of the complements. It obeys the generalized De Morgan laws. The complement of the supremum equals the infimum of the complements. The complement of the infimum equals the supremum of the complements. Or we can say the complement of the join equals the meet of the complements. The complement of the meet equals the join of the complements. Next, dual lattice. Determine whether H is a dual lattice. As we have known that the double negation law holds, the De Morgan laws hold, so this algebraic structure is a dual lattice. Next, density. Determine whether H is a dense lattice. A lattice is called dense if for all elements a, b in L, a is less than b, then there exists an element c in L such that a is less than c, less than b. Is 8 a dense lattice? Yes, the lattice is a dense lattice because of the density of the real numbers. Now we have known that each pair of elements has a supremum and an infimum, and the poset is a lattice. This is the algebraic structure induced by the lattice. Of course, it obeys the idempotent laws, the commutative laws, the associative laws, and the absorption laws. This lattice is bounded with the greatest element 1 and the least element 0. And we define a unary operation, complementation. The complement of A is 1 minus A. The algebraic structure, the closed interval from 0 to 1, together with the two binary operations and one unary operation, satisfies the following rules: the distributive laws, the infinite distributive laws, the De Morgan laws, and the generalized De Morgan laws. Also, it obeys the double negation laws, together with the De Morgan laws, which makes it a dual lattice, and it is complete. Now we can answer one of the questions we put forward at the beginning of this lecture. Is H a Boolean algebra? A Boolean algebra is a complemented lattice together with distributivity. We know that the complementary laws do not hold in this lattice. So this lattice is not a Boolean algebra. Is it a soft algebra? A soft algebra is a dual lattice, together with boundedness and distributivity. This lattice is a soft algebra. Is it an optimal soft algebra? An optimal soft algebra is a dual lattice, together with density and infinite distributivity. It is an optimal soft algebra. The closed interval from 0 to 1, together with the two binary operations, the supremum and the infimum, and the unary operation, the complementation, is an optimal soft algebra. In this lecture, we have talked about the algebraic structure on the closed interval from 0 to 1, which will be very important in this course, especially in next lecture. Next time, we will talk about the algebraic structure on the fuzzy power set. Thank you.